Hello, everyone. My name is Giacomo Beccari. I'm going to very quickly introduce myself. I'm very glad to, on behalf of the ESO Science and the Director of Science, to welcome you to the second episode of the Hypatia Colloquium series. We are very happy to have today the two young astronomers who will tell us about fantastic science. I'm going to just give you very briefly some technical details. As you know, you can join the colloquia through basically watching live stream on YouTube or by joining us in the Zoom, in the virtual world of Zoom. To do that, basically you need to register, and registration can be done at the Hypatia Colloquium pages. The questions, so there will be, each speaker will have a 30-minute slot, 20 minutes of talk plus 10 minutes of questions. Everyone is very welcome to make questions. You can do so if you are in Zoom by using raise hand feature, and then you will the chairs that is going to be today Lucas and Teresa. They will be happy to give you the word, or can be done if you are on YouTube by leaving your question on the chat on YouTube, and then we will forward the question to the speaker. If you do not, so if you do not have an account on YouTube, so if you don't want to leave your question on the chat, you can also send your question. If you go to the Hypatia pages, the link is available from the YouTube channel. You go to the pages, there is a question, basically a form that you can fill where you can write your question. You press send, and then we will monitor the question live, and then you can pass them to the speaker. And with this, I think I'm finished. Please enjoy. We sure will be exciting, and please don't forget to register for the next events. And I leave the word to our chairs of today, Lucas and Teresa. Thank you very much.
Thank you, Giacomo. Good afternoon, everyone. It's a great pleasure to chair this another session of Hypatia Colloquium, a colloquium that's created to promote early career astronomers to showcase their world-class research to the world. They were selected in a very competitive process, so congratulations to both our speakers today who will be presenting. And the first of them will be Indranil Banik from the University of Bonn. Indranil finished his PhD at the University of St. Andrews, specializing in distinguishing the different properties of standard modified gravity and particularly testing them observationally. So I'm very excited to hear more about this today. Indranil now is a Humboldt Fellow at the University of Bonn. And with that introduction, I will give you the floor, Indranil.
Yes. Everything okay?
Yes, perfectly.
Okay. So I'd like to talk about a recent publication led by a master student, Elena, also in Bonn. And this is about using galaxy clusters to test LambdaCDM cosmology. So this is the journal reference. Now, the basic idea is that structure forms hierarchically out of the density fluctuations observed shortly after the Big Bang. You form stars, galaxies, and galaxy clusters over time. Now, in the correct cosmological model, it is going to be possible to statistically predict when these structures all formed. That's one important constraint. Now, as explained earlier, we'll be focusing on the galaxy clusters. What actually do we see? So galaxy clusters come in a wide range of masses, but in this talk, I'm going to be talking about the most massive ones because these pose a particular problem, as we'll come on to. So in recent years, surveys have found various galaxy clusters. For example, the Bullet and various others will be focusing on the Gordo galaxy cluster in particular. Now, this is at a very high redshift and with quite a high mass. In LambdaCDM, so the standard cosmological model, there shouldn't be clusters more massive than about 1.7 quadrillion solar masses. So objects like El Gordo, you can see straight away, shouldn't be very common at all. So what we did is we tried to quantify how problematic the observation of El Gordo is for LambdaCDM. So just to give a brief background on what we're trying to match, first of all, there's the redshift, which is known to very high precision. We have two subclusters that are colliding. So El Gordo is a colliding galaxy cluster sort of pair with a total mass and mass ratio. This is a major merger. The masses are not too different from each other. There's a high infall velocity. Perhaps the reason it was discovered is that it's the most X-ray luminous and brightest Sunyaev-Zildovich galaxy cluster at this redshift. So that's El Gordo here. Now, one important thing that we'll come back to later is that there's this twin-tailed morphology, which is not so easy to produce. For example, you don't have a twin-tailed morphology in the bullet, but you can see it clearly here in the X-ray. And actually, there's also the optical data in the background, the red galaxies. So there's one cluster here and one cluster here. So that's the El Gordo, which is perhaps a bit clearer here. This image has been processed a bit more, but this gives you hopefully a scale of the problem. Now, to quantify the likelihood of El Gordo, we followed a two-step procedure. If we try to understand the detailed observations of El Gordo, like the detailed morphology, you would need a hydrodynamical simulation, which is quite expensive. So you would start with various different pre-merger configurations, different masses, mass ratios, this sort of thing, but in a non-cosmological context, and try and match the detailed observations. Now, this has been done before. What we thought we would do is check if the pre-merger configuration is in fact consistent with the CMB. If you assume the CMB had evolved forward to the pre-merger configuration according to LambdaCDM. Now, to address this, we use cosmological n-body simulations, because in this stage of the process, the details of baryonic physics, hydrodynamics should not be too critical. You just end up with two masses at the right separation and velocity. But if you try to advance the n-body simulation all the way up to here, it wouldn't have enough resolution to match the observations in detail. So yeah, there's this two-step procedure, and we focused on this aspect. This aspect, however, is what we'll discuss first, because this was done earlier. The idea of these hydro simulations is to have two masses which undergo flyby, and hopefully they reproduce the observed configuration, which is after pericenter. That much is relatively clear. But exactly how much after and which angle we're viewing it from, these things have to be varied. What's the purpose of varying these quantities? It's to match observations. So in particular, the X-ray luminosity, the fact that there's a single bright X-ray peak and a twin-tailed morphology, which is not trivial. And of course, the sky projected distance between the X-ray and Sunyaev-Zildovich centroids. Yeah, so these are some of the main constraints on the problem. So we used the simulation run by Zhang et al. In 2015. This is one of the most recent and most detailed studies, and also the one which I think got the best match to El Gordo, at least in terms of the detailed morphology. They considered two types of model, very energetic head-on collisions, so with a very small closest approach distance, which allowed a slightly lower mass, but a very high speed was required in this scenario. This, however, did not reproduce the twin-tailed morphology. So although we do consider model A in our paper, we mainly focus on model B, which is a perhaps more realistic, more off-center collision, the higher total mass. Also, the mass ratio is a bit more realistic. The masses don't need to be that close to each other. Importantly, this would reproduce the twin tail morphology. As you can see here, this is a simulated image, but it actually does get the twin tails. So we'll be focusing on the model B. Now, as I was saying earlier, although model B works to reproduce the detailed morphology, it may be that such a high mass galaxy cluster pair with such a mass ratio does not occur in LambdaCDM cosmology. This question was not addressed by Zhang et al. In 2015. So to address that, what we did is we used the Jubilee simulation, which is the largest suitable simulation for this, with a volume side length of 8.5 co-moving gigaparsec, using WMAP parameters. This was used to find the halos in the Jubilee simulation. So the redshift, we have snapshots at these redshifts. For this project, we didn't need the redshift 6 snapshot, but we needed these 3 snapshots. And especially this snapshot is obviously quite critical for this project. The simulation has quite a good resolution. The particle masses and the lowest resolved halo mass are all much smaller than El Gordo, which is about 10 to the 15 solar masses. So you can see here that this is already 20 particles worth. So this is well resolved in the simulation. Now, to do the statistics, we considered galaxy cluster. First of all, we consider only galaxy clusters. So we require all the halos that we consider to have at least this much mass. So that removes galaxies, basically. Then we find pairs with a tree-based code to avoid searching, like doing an order n squared operation, basically. The idea, though, is to compare only pairs where the Keplerian orbital period is below 100 times the age of the universe. So that's very not very restrictive at all, but still it reduces the computational cost a great deal. Because you only consider clusters within 40 megaparsec rather than within about 6 gigaparsec. Then we also require, crucially, that the galaxy cluster pair is approaching each other, that they've turned around from the cosmic expansion, and they have a similar mass. So the ratio of the highest to the lowest mass is below 3.6. Now, the important thing, so there's certain other conditions that we also need to impose, and we did these sort of in stages. First of all, we're focusing on the Redshift 1 snapshot because we're talking about the pre-merger configuration, not the observed configuration. Should be a slight time lag. Then the ratio between the infall velocity and the escape velocity at twice the sum of the virial radii needs to be 1.24 or larger to have a more extreme event. And of course, one of the crucial constraints is the total virial mass, which we wrote in this way is the m tilde needs to be at least 15.5. So you need a total mass of at least 3.2 quadrillion solar masses. Now, what this does is shown here as the number of pairs above or equal to a certain mass versus the mass. So obviously this is going to be a declining function. What we found is that you can fit it very well with a parabola. So that's very straightforward. Now this orange curve shows what happens if you require just v tilde, this ratio greater than 0, but this green line is the one we typically use. You can also require the impact parameter is smaller than the one in the Zhang simulation, but this does not really change the results. So to be more conservative, we just use the green one, which uses this condition, and ignore this one. So why it's in gray. Now, what we then did is conduct what is called light cone tomography. So we consider a grid of mass and scale factor and we apply a quadratic fit, as I was showing earlier, but we do this at 3 different redshifts. So you get a value for these coefficients C0, C1, and C2 at all these 3 redshifts. Because we have 3 different values for C0 at 3 redshifts, we can extrapolate to find the value of this coefficient at any other redshift by using a parabola. So we can obtain C0, C1, and C2 at any A, and therefore we can find out the number of clusters more massive than some mass at any A. And then, of course, we have to find out in each pixel in mass and scale factor along the past light cone of a redshift 0 observer, how many cluster pairs there should be. That is shown here, the scale factor and the mass. Now, the important thing to understand is that most cluster pairs should be around here. This is sort of the 1 sigma and 3 sigma confidence limits, 5 sigma. El Gordo is up here. So El Gordo is a 6.16 sigma outlier to standard cosmology, which means the probability is below 1 in 1 billion. So this is the main result of our work. Now, we also combined this with the bullet cluster, which is somewhat similar to the El Gordo, although much less extreme. In the bullet cluster, which you probably heard of, this offset between the X-rays and the weak lensing peak, which is where the gravity comes from. To reproduce that, you need a high collision velocity. That's the only way to generate enough gas drag to separate the collisionless component from the collisional gas. Now, it's previously been shown that there's a 10% probability of finding a bullet cluster analog out to redshift 0.3, but this is for a survey covering the whole sky. If in reality, the bullet cluster is found in a survey covering 5.4% of the sky. So of course, you can just multiply that by 5.4%, and that makes it a 2.78 sigma outlier. So the bullet cluster is not a major problem for LambdaCDM by itself, but if you combine the probabilities, so you combine the chi-squared values for the e.g. the El Gordo, we have 6.16, and the bullet cluster 2.78, get a combined probability. So this is what's shown here. If you combine the probabilities, you get 6.43 sigma. And if you assume that the surveys which discovered El Gordo and the bullet cluster covered the full sky, then that will reduce the tension slightly to 5.66 sigma. But clearly, the LambdaCDM model must be rejected at greater than 5 sigma confidence, at least with the condition on the velocity, which is necessary. However, if you require the velocity to merely be greater than 0, then the tension is much less. So one thing we did is look at the effect of the velocity constraint. So first of all, one thing to understand is that it's possible to reproduce the twin-tail morphology pretty well at a collision velocity of 2,500 kilometers per second. So this is the observation and this is the simulation. Now, if you use 1,500 kilometers per second, there's basically no twin-tail anymore. It was concluded by these authors that the lowest plausible collision velocity is 1,500 kilometers per second. You can't really have less. So what has been plotted here is a statistical significance, a number of standard deviations equivalent for a Gaussian as a function of the infall velocity. And what I was showing previously is the results for 2,500 kilometers per second for El Gordo and combined with the bullet cluster. If you go to 1,500 kilometers per second, then the tension is slightly below 5 sigma in this case, but it rises above 5 sigma when you combine with the bullet cluster. So this will still be about a 1 in a million event, and worse with the bullet cluster included. And lower velocities will not reproduce the observed morphology, so the X-ray photograph. So what we can conclude from this is that El Gordo will contradict LambdaCDM at any plausible collision velocity. Another problem with just reducing the, another thing we consider in the paper is reducing the mass. And this has been argued carefully that lower mass will reduce the X-ray flux. which will then not match observations, one can compensate with a higher velocity, but that makes the situation worse. And the mass is in any case constrained by weak lensing. Other thing is that we're focusing on the model B case of Zhang et al. 2015. The model A case, which does in fact have a lower mass, is also in more than 5 sigma tension with LambdaCDM, but it does not reproduce the morphology as well. We considered various other things in the paper, such as whether we had enough clusters to do this properly. But Jubilee is a very large simulation box, and the mass functions that we were using, although these are sort of analytic fits, they're based on more than 15,000 pairs, and they need to be extrapolated up to the El Gordo mass, but only by about 0.6 dex. And the fit is itself over about 1 dex almost. So we think that our statistical approach is reasonable and not much subject to Poisson noise. We also consider different mass range for the parabolic fit, so only fitting towards the high mass end rather than the entire mass range. In other words, changing the lower limit, but this doesn't affect the results very much. I haven't got time to discuss it in this talk, but we considered how rare El Gordo would be in a MOND cosmology. So there is a viable MOND cosmological model, which previous simulations have been done in it. So that's called this new HDM cosmological model. CATS Plus 2013 performed n-body sort of simulations in this model, and they found, interestingly, 1 El Gordo analog in the simulation volume. So although this was from 2013, they still use the correct parameters for El Gordo because these have been stable for a very long period of time. So this is obviously quite remarkable because we found very, very few analogs, about 10 to the minus 8 analogs in a volume which is about 1,000 times larger than their simulation. The important thing is, so I haven't described the power law analysis in this paper, in the talk, but in the paper there's a power law analysis slightly different from the light cone tomography. And if you try to apply that, you can find the effective volume covered by the survey, like how much volume does it cover, and compare it to this. And the result of that is that the 1 El Gordo analog they found would correspond to 1.16 El Gordo analogs in the survey volume. So in other words, according to this MOND cosmological model, there should have been 1.16 El Gordo analogs in the cosmological, in the survey volume, which means therefore that the new HDM model gets the right order of magnitude for the frequency of El Gordo-like objects, whereas LambdaCDM is approximately 10 orders of magnitude off. So that's what we mean by a 6 sigma tension. Now, that brings me on to my conclusions. So the pre-merger configuration of the El Gordo galaxy cluster collision has been found using hydrodynamical simulations, but these do not consider the cosmological context. When we do consider that using Jubilee, we find that the model parameters contradict LambdaCDM at more than 6 standard deviations. Based on previous results, the Boer cluster is in about 2.8 sigma tension, which combined with this gives a 6.4 sigma tension. Now you can try and look at it this various other ways, vary the mass, the collision velocity of El Gordo, but for any plausible value, the tension is more than 5 sigma. However, such an extreme galaxy cluster collision as El Gordo, and indeed as the bullet, as shown by Katz et al. 2013 as well, would occur in the MOND, this new HDM cosmology. You expect 1.16 El Gordo analogs in the survey region, which is about right compared to the 1 that was observed. So if you want to find out more, you can look at the paper or also check out the Dark Matter Crisis blog, where Ellen has described the work in a bit more detail. Thank you.
Thank you very much, Indranil, for this very interesting talk with some bold results, but very well justified. So I was very excited to see that. Let me remind you that you can either raise your hand on Zoom or send a question by form. And while you are doing that or typing your questions, I will ask a question that I got already from Tim Schrabak. And the question is, how sensitive are your results to current observational uncertainties regarding the properties of El Gordo? And what future observations would you like to see to tighten the constraints on the cosmological model?
This is a very good question. First of all, I would argue that the properties of El Gordo have been known very well since the work by Menantiu et al. 2012. So I think the uncertainties are not very large. For example, regarding the twin-tailed morphology here. However, additional observations would help. Where they would especially help is if we can constrain the weak lensing mass more precisely, because then we would be able to definitively rule out model A if the weak lensing mass stays the same, but the uncertainties shrink. And then if we know for sure that it's model B with a high mass and an off-center collision, then one can do like a one-parameter search for different infall velocities, see which, and generally just really determine what is the minimum infall velocity that will look right. And therefore, if that is reasonable in LambdaCDM. So yeah, I think the weak lensing is probably the most important.
Right, thank you very much. And we have a raised hand from Hussein Hagi. If you want, you can unmute yourself and ask a question directly.
Okay. Thank you very much, Indranil, for a very interesting talk. And it's interesting to see another evidence against LambdaCDM. I was wondering, I mean, did you get any reaction from the LambdaCDM community side related to your paper?
Well, I was actually asked like a similar question there regarding the follow-up observations. I haven't got, yeah, I haven't, the only main concern that's been raised is perhaps the cosmological parameters. So we assumed the WMAP parameters in Jubilee. Maybe if you use the Planck parameters where omega m is 0.31, it'll change the results slightly. But yeah, so people in the LambdaCDM community are aware of the results, but they haven't identified any major concerns with this.
Yeah, it seems even baryonic physics cannot help to solve this problem.
No, because this is on a much larger scale. Yeah, the baryonic physics won't really. I mean, what I mean by that is that one has to model the shock, but the small scale sort of stellar feedback in galaxies is not important. The other thing to realize is that as people have done more and more simulations, the pre-merger configuration required for El Gordo has remained stable. So if you look up papers from 2012, you'll get basically the same results as what Zhang got in 2015, and which is the most recent. So yeah, it's not very sensitive to modeling assumptions.
Thank you.
Yes, and thank you very much for this question. And we have another question from Dietrich Bada. So please unmute yourself, Dietrich.
Yeah, this was a really very exciting talk, very well presented. So thank you very much for that, and congratulations on this interesting work. I'm a little bit worried, and partly repeating the first question, whether you started the analysis with some bias in your mind, because you picked model B, which has a higher mass.
Yeah, but that's because Nagatol 2015 picked the model B. They preferred the model B.
Yeah, and then you studied in the simulations only clusters which have a mass of 3 × 10⁻15 or more.
No, that's not correct. In the paper, we have a subsection discussing the model A as well. And we showed that model A falsifies LambdaCDM at more than 5 sigma.
Yeah, I heard you say that. But would one not do the analysis symmetrically about the most plausible mass? At least to the level of 3 sigma. And if you are claiming and finding a tangent at the 6 sigma level,
yeah,
should you not go to a similar large error bar in the mass?
Well, hang on. One can consider different masses, and the tension is more than 5 sigma in both cases. You really can't. The Zhang et al. 2015 article showed that you really cannot get a realistic match with a lower mass. This is like the lowest plausible mass. So you're only considering the tension from like is the pre-merger configuration plausible in LambdaCDM? In reality, one also has to consider an additional sort of chi-squared penalty from how poorly the model reproduces the detailed morphology of El Gordo. And if you like, we've assigned a chi-squared penalty of 0 there. In reality, that is perhaps reasonable for model B. For model A, that's already not ideal. And for any lower mass, the pre-merger configuration would be legitimate in LambdaCDM, but the detailed morphology would not work. So essentially what I'm trying to say is you can, at a lower mass, this step becomes much easier to fulfill, but this step will fail.
Okay, thank you. And so let me move on to the last question from Enrico Garaldi from the Max Planck Institute for Astrophysics. And the question is, interesting that the new HDM cosmology has the right frequency of El Gordo clusters. How does this cosmology score in terms of other observables like CMB power, spectrum, gravitational wave velocity, etc.?
This is a good question. So let me just say that this new HDM cosmology has been discussed in more detail in another article, MNRS 4992845, Hasselbauer et al. And what we've shown there is that it should fit the CMB quite well. This model was actually proposed in 2009. And the idea is to have sterile neutrinos whose relic density is the same as this cold dark matter in LambdaCDM. And we also showed that because the gravitational fields were much stronger than A0 at that time, one would get essentially a standard CMB, a standard expansion rate history. And one should also get the right Big Bang nucleosynthesis to work. But yeah, that's described elsewhere in more detail. So this will contain a link to that. But it's not clear that it will match sort of all observations perfectly. But what I would argue is that the main early universe observables like the CMB and BBN will be fine. The large scale structure, because it's very different to LambdaCDM, well, we don't know if that will work. NeoHDM seems to work better in that regard, as I've argued in this talk. And the other thing I wanted to say is the new HDM will basically just reduce to MOND in galaxy scales, because the neutrinos will essentially not cluster in galaxies. And as a result, the new HDM will be much more consistent than LambdaCDM with galaxy scale observations, where it's well known that MOND works much better.
Yes, thank you very much, Indranil, and thank you all for the questions. Let me just remind you that you can find contact to Indranil on a Hypatia Colloquium webpage with his CV as well. And I encourage you to get in touch. But now we're going to move to the next talk, and I'll give chair floor to Teresa Panek-Carreno, a ESO PhD student.
Sorry, Lukasz, I will just jump in. Sorry, very to apologize. So there is something wrong with the chat on YouTube. I was trying to fix it. But I failed miserably. This is completely my fault. I would like to apologize with the speakers, first of all, and also with the attendees. Sorry about that. But as I said, you can still send, as few people are doing, you can send your questions if you go to our webpage, www.eso.org/ESOHC, like ESO Hypatia Colloquium, then you go directly to the Hypatia webpage, and then on the right-hand side, you see send question to the speaker, and there is a form. You can it's very short, you quickly fill it, and then you send it, and then I receive the email and I can pass it to the chairs. I'm sorry about that. I promise I will fix it for the next time. Just wanted to clarify. Sorry, and congratulations to Indranil. Also, one last thing that I completely, in the rush to giving the word to Lukasz, I forgot to introduce. Lukasz is our ESO fellow. Lukasz started the fellowship last year with us, and Teresa, which is going to be the next chair, she is our enthusiastic student at ESO, PhD student, and we are very happy and thankful to them for chairing these sessions. Thank you very much. Sorry.
You can also email questions to the speakers, I imagine, as well.
Yes, of course.
Yes, of course.
Yeah, as Łukasz said, all the contact details of both Indranil and Rajika now can be found in the Hypatia Colloquium webpage. So if you have any further questions, you can, of course, forward it to them. So now, as Łukasz was saying, we will have the talk by Rajika Kuruwita. She is a PhD from the Australian National University and currently working as a postdoctoral researcher. She is a European Union Interactions Fellow in the University of Copenhagen, where she is interested in studying and researching the formation of binary and multiple star systems via numerical simulations. The talk that we will hear is titled Accretion Behavior During Binary Star Formation. So again, I encourage you to ask any questions through the form or raise your hands in the Zoom. Thank you, Rajika. You can start sharing whenever you want.
I will share screen now. And I guess everyone can see it. So, yeah. Hi, I'm Rajika Kuruwita. I'm a postdoc from the University of Copenhagen, and I'll be talking to you about simulations of binary multiple star formation. But in this talk, I'll mostly cover work that was published last year, Kuruwita et al. 2020, about accretion behavior and how it evolves with eccentricity. So let's continue. That. So multiple star systems are very common. From this plot from Mo and Di Stefano, we see that the single star fraction, this red line, decreases as a function of primary stellar mass. That's because it is overtaken by the binary fraction, the triple star fraction, and the quadruple star fraction. Now, this work mostly looks at main sequence stars, but observations have found that a single molecular core produces on average 2 to 3 protostars. And we also see that multiplicity evolves as a function of protostellar classes, with multiplicity being higher in class 0 objects and dropping from class 1 to main sequence stars. This decrease in stellar multiplicity over protostellar stages indicates that these young systems disintegrate through various processes, maybe dynamical interaction. And while these systems are evolving, the components host disks. I want to study how multiplicity influences how the star and disk system evolve, and particularly accretion on stars and the survival of these disks. One problem that was discovered in the 90s by Kenyon et al. Was the luminosity problem. This problem states that the observed luminosity of low mass protostars is much dimmer than that predicted if they accreted their mass at a steady rate. A couple of main solutions to this problem is that, one, stars form much slowly. So as a reference, Kenyon et al. Used a timescale of 0.1 to 0.2 million years. Or 2, mass accretion is episodic. Or it could be a combination of both of these. We have thought for some time that accretion outbursts could play a role in star formation because we have observed such outbursts from young objects with disks. The two main types of observed outbursts that we see are FU Orionis and EXO outbursts. FU Orionis have timescales of well, decades to thousands of years, or hundreds of years to thousands of years, and have accretion rates as high as 10 to the, that's meant to be 10 to the minus 4, yes, that's right, 10 to the minus 4 solar masses per year. Well, EXOs are much shorter lived, so on the order of months to years, and don't have as strong as an accretion rate during their burst period. So both of those, while we see these outbursts, we have thought for a long time that they are part of the typical accretion history of protostars, with the initial high accretion rates being attributed to the infill of the envelope, and the later stage accretion rate probably being due to accretion from the disk. But what causes these accretion bursts? So there's a few different theories that have been proposed to explain what triggers these events. Examples are gravitational instability in disks, tidal interactions with a companion, thermal instability, disk magnetospheric interactions, many other theories as well. But in this talk, I'll talk mostly about this tidal interaction with a companion. Now, the binary trigger hypothesis, or the tidal interaction with a companion, has been around for a long time, especially given that FU Orionis itself is a binary, and it could have actually had a tertiary companion that was recently ejected based on these observations from Reperth and Aspert 2004. So this is FU Orionis, and this is a companion that might have been ejected from the system. We have also seen triggered accretion in other young binaries. So these are two TWA3A and DQ tau, are two very short period binaries. They have periods of 34.8 and 15.8 days respectively. And when we phase fold their accretion, we see these peaks in the accretion rate near periastron. So this is just a simulation, a hydro simulation from a repo, trying to fit to these observations. But the observations, yeah, show this clear peak that has been phase folded over many, many orbits. And we also see it in a few other short period young binaries as well. I was also seeing triggered accretion in some of my simulations. So this is a separation of some binaries that I was simulating. There's a black, red, and blue, and this is a total accretive mass. The solid line is the total accretive mass, and this is the accretive mass of the components. But we see that we get these jumps in the accretion at various times, and when you look at the separation, they pretty much correlate with periods like when the system was at periastron. And I thought this was very interesting. I'd like to investigate it some more. So I ran these simulations a bit longer, and I'll explain my simulation setup. My simulations were run in the magnetohydrodynamic code Flash. It uses ideal MHD if you're interested. And my simulation setup was just this box, and it started out with a cloud of about 3,000 AU radius. It was one solar mass, and it starts in pressure equilibrium with some gas outside it. This cloud is given solid body rotation, and there is a magnetic field that is threaded parallel to the z-axis. So in this little schematic, it comes out of the page. And to encourage the formation of a binary, I impose a density perturbation, which is described by this little equation here, where rho naught is just the density of this cloud if it was uniform. So the result of this is that we get over densities at particular angles and under densities at others. And this is just to help see the formation of the binary. On top of the solid body rotation of the cloud, I also impose some turbulence just on the initial velocity distribution. So I run two simulations, one with turbulence of Mach 0.1 and one with turbulence of Mach 0.2. And the resolution of the simulation that we look at mostly in detail is just under 2 AU. So the results of the simulations, I'm just going to play this movie. So the density will be described by this bar. These blue lines show the magnetic field, and the mass of the two stars will be annotated in these two corners. So this is for the lower turbulence simulation. This is for the high turbulence simulation, which I call T1 and T2 further on. So let's just have a look at how this evolves. So when the simulation first starts off, we get these filaments that kind of form, and the two stars form along that and fall towards each other. They both have their own individual circumstellar disks, but as they approach each other, these disks are being disrupted. And while they're interacting, so the gas is being thrown outwards. The arrows show the velocity field. And in the more turbulent simulation, we see that this large circumbinary disk starts to form pretty nicely, and the less turbulent one, that's not as obvious just yet. This is really handy. It's good because other simulations of disk formation generally show that having more turbulence produces larger disks. So that's good. But yes, by the end of the simulation, which is about 6,000 years, sorry, I didn't annotate the time, we get this nice circumbinary disk forming. So let's have a look at how this binary system evolves. Here I plot the separation of my two systems, T1 and T2. This is the accretion rate of the total system and the eccentricity as we evolve. And from this, we kind of already see some episodic accretion. We get these spikes in accretion happening, and they look like they happen near periastron. But it's kind of difficult to talk about this behavior just by looking at this. So I figured the best thing to do is probably try to phase fold this as best as we can. So in the phase folding, I identified times of periastron and apastron, and I made 10 time bins between each of them and calculate the average accretion within the time bins. But then, yes, when you add those together, you get 20 phase bins between periastrons. So once I could bin that, I could phase fold it, but as you can see from here in this plot, the system is evolving a lot over the entire course of the simulation. So it's not appropriate to phase fold over that. So instead, I defined some eccentricity bins over which we can phase fold a few orbits. The eccentricity bins are defined so that there is at least 3 orbits in each bin. So the T1 simulation has more bins than the T2 one, and that's because the T2 simulation inspirals very quickly, so there is not many orbits to sample as it inspirals, whereas the T1 inspirals a bit slower. So once I phase forward that, what did that look like? Well, this is the phase forwarded curves for T1 and T2. So this is the x-axis is just the phase, and this is just the accretion rate, and it moves from high eccentricity down to lower eccentricity. And we see from these plots that, yeah, near periastron, we do get these peaks, and the strength of it seems to decrease with eccentricity. So we see that in the T1 simulation. Also in the T2 one, we do also get these peaks as well. So the green is the total accretion rate, but I also tried to plot the accretion of the primary, which is in blue, and the secondary, just to see if at any times one or the other was a dominant accretor and how that could change its behavior. And we don't seem to observe anything like that, but the binaries that I form in the simulation, they have mass ratios, which is pretty close to 1. So maybe this behavior could change if the mass ratio was a lot lower. But yeah, so I phase folded these curves, and the one thing I wanted to find out was if there was any dependence on the strength of the accretion with eccentricity. So I have to define how strong this episodic accretion is. So I defined this beta, which is simply a ratio between the average accretion rate during the burst and the average accretion rate during the quiescent phase. So the burst is defined as a period between 0.8 and 1.1 phase, and the quiescent phase is defined between 0.2 and 0.75. So when I did that for these different eccentricities, what did I get? I got this. So beta of 1 basically means that there is no measurable episodic accretion, but anything much greater than 1, we do get episodic accretion. So I guess before you do this experiment, you would typically think that with higher eccentricity, you would get stronger episodic accretion, which is kind of what we get with the T2 simulation. We kind of see that there is no measurable episodic accretion, these low eccentricities, but it gets stronger and stronger. But then it drops off at these highest eccentricities. Interestingly, we see that with the T1 simulation, we get this plateau. So it doesn't seem to grow much stronger. Maybe that could suggest that there is some dependence on the turbulence in the disk and the strength of episodic accretion. But typically what we find is that for when the system is above an eccentricity of 0.2, we seem to observe this episodic accretion. We also ran with this paper a convergence test. We ran the simulation with a few different levels, and I tested to see if this beta was converged. Yes, I'll get back to that. So this is our working simulation was this level of refinement 12, which is these orange points. And we see when we go to higher and higher resolutions, we get stronger and stronger episodic accretion, mostly around this middle eccentricities. But we do also find with the higher and higher resolution simulations, the binaries inspire a lot faster. So it makes it harder to sort of sample this behavior over the different eccentricities. But yes, we did find it peculiar that at the highest eccentricities, this episodic accretion was a bit decreased. And we suspect that it's because the separation at periastron is smaller or comparable to the size of the disks. So when the system approaches periastron, the circumstellar disks are violently disrupted, which can suppress the accretion. Yes, so we could see that we're getting this episodic accretion happening. There doesn't seem to be any clear trend with eccentricity, but we wanted to know what exactly was the trigger of the accretion. So with these higher resolution simulations, we decided to look at this highest resolution simulation, which had completed a couple of orbits. So this has a resolution of 0.5 AU. And these are some slides which are zooming into the first periastron. So this is the primary and the secondary, and we have these density contours which span 2 orders of magnitude. And what we see is as the binary approaches periastron, the circumstellar disk is distorted towards the companion, and the spiral wave is excited, which triggers the accretion event. But then as the binary is approaching periastron, there's some compression in the disk, and then material is very violently disrupted and thrown outwards. So we could see this sort of happening, but to sort of get a better idea of what exactly is happening, I decided to plot the angular momentum, or the orbital angular momentum evolution of the system. So on this top panel, I plot the accretion event. So this is the accretion rate of this event, and this is just the separation. So the periastron happens just a bit past 1500 years. And here is the orbital angular momentum of the primary and the secondary. And we kind of see that as they're approaching each other, they increase in angular momentum. And we think this is where what we saw in the plot before, the companion is getting angular momentum from the outer disk because of their differing angular velocities. But then they kind of enter periastron and lose a lot of angular momentum because they start throwing out circumstellar material outwards. So ultimately, the accretion event is triggered by this angular momentum exchange, causing between the circumstellar material and the orbital angular momentum. So this was very neat to get to the bottom of, but we thought we'll try to compare our observations with some compare our simulations with some observations. So unfortunately, the timescales of FU Orionis and XORs, so it's going to be FU Orionis, is too long to be phase folded. So we thought that we would, look at the work from Benjamin Toffelmeyer, so for the DQ tau and TW hydra. So it could be debated whether it's appropriate to compare our simulations with these very short period binaries. But this simulation from Munoz and Lai is it's a scale-free binary simulation of binary stars accreting from a circumbinary disk. So it could be applied to low mass binaries or high mass binary black holes. So yeah, we thought we'd just give comparing our simulations to these observations a try. Now, the first problem is that because these binaries are later evolutionary stages, so class 2, their accretion rates is very low, whereas the accretion rates in my simulation were quite high. So the first thing I had to do was sort of normalize both of these by just integrating onto them and normalizing them, then I could compare them. So the results of this, yes. So once I normalized everything, I could compare my phase folded curves with the observations. I picked the phase folded curves from the eccentricity bin, which matched the eccentricity of these two systems. So they're actually the same. They have very similar eccentricities of about 0.6. And the results is this, and I apologize that it's so messy, but these solid lines is the observations, and the transparent lines are my simulations. So we see that T1, this blue one, actually gives pretty good agreement between the accretion rate during the quiescent phase and the peak accretion rate, while our more turbulent simulation underestimated and overestimated the accretion during the quiescent and peak burst phase, respectively. But what is peculiar is that the timing of our peak is offset from the observations. It's a bit earlier compared to the observations. But despite that, the fit looks pretty good in terms of the strength, like how the accretion rate varies over the orbital phase. And this is, yeah, the simulations of Munoz and Lai. Now, one thing that could be changing the timing of the peak is between our simulations and the irreparable simulations is that we include magnetic fields, and magnetic fields can increase the gas viscosity, which leads to shorter viscous timescales between when the circumstellar disk is disrupted and when the accretion event happens, but it's not entirely clear from this work. But it is very interesting that despite the differing evolutionary stages, there is overall good agreement between the shape of the simulated curves and the observed binaries. And this suggests that accretion behavior at periastron for eccentric binaries is largely independent of the orbital separation, and signs of episodic accretion may be detected in long period binaries despite, and yes, but there is still some work to be done for getting the specific timing of our burst and to match with the observations. So what does this say about the binary trigger hypothesis? Well, from our work, we kind of found the burst period is about 30% of the orbital period. That means we can very easily retrieve the duration that FU or an XOR outbursts have just by scaling the orbital period. So for orbital periods greater than 40 years, we get burst periods of greater than 10 years. And for orbital periods less than 8 years, we get burst periods of less than 2 years. So that's nice. But the problem is that we don't quite retrieve the strength of the accretion observed in FUs and XORs. So yeah, FURNs, they have accretion rates about 100 times greater than the quiescent phase, and XORs 10 times greater. So from our resolution study, we were entering the realm of XOR Orionis outbursts. And maybe with even higher resolution, we could push into FU Orionis, but that's not clear from this work. But despite this, with the observations that we do compare with, we do get overall, well, yeah, we do seem to find that episodic accretion probably does happen in long period binaries, and the behavior of that might be similar to what we see in short period binaries. So if you want to read more about this work, you can look at my paper, Kuruwita et al. From 2020. But yes, the next steps, well, my simulations I just talked about, they had very ideal setups, and the universe is, well, very turbulent. As you can see, you get ionization from big stars and jet feedback. So my next steps was to do some zoom-in simulations with Ramses from this giant turbulent cloud box to maybe explore different formation pathways. So Tobin et al. 2016, based on this observations of young multiple systems in Perseus, they observe this bimodal peak and attribute this peak to core fragmentation, this peak to disk fragmentation. So I'm hoping from these zoom-in simulations, I can look at these different formation pathways and see if I can replicate this. But for now, I will leave you with my conclusions, and I'm sorry for going over time a little bit.
Thank you very much, Rajika. It was a really, really interesting talk. I really enjoyed it. So just if anyone from the Zoom wants to ask a question, you can raise your hands and then I will let you speak. While you think about questions, I actually had a question myself. So I don't know, or maybe you explained it and I didn't really catch it. You talked at one point about the stellar mass that your binaries had in your simulations. And I don't know how this compares to the mass that the observations you compared them to had, and if that could be the cause maybe of any discrepancies between your simulations and the observational results.
That's okay. I did remember looking at this. So the observed binaries are quite low mass. I think they're lower mass than the sun. And our simulations by the end of it, they were, I think, oh, if we can go back to the accretion plot. I don't know if I actually plot how much they have accreted. Maybe if we just look at this. By the end of this simulation, they're not that massive. So yes, but I can look at the paper to see if there is a significant discrepancy between the mass of what we observe and what the observations we're finding.
Yeah. I don't know if anyone else has. Okay, so Giacomo has a question.
Yeah, hi. Thank you very much. Also from my side, really, really beautiful work. I have a question, so two questions in fact. One is exactly on this plot and this simulation. I wanted to, because I couldn't, maybe you mentioned the time scale. So on which time scale do you expect the interaction to bring through a disk, basically?
So how quickly do the disks form? Is that what you're asking?
Yeah, exactly. So you have the two stars, they come in, then you start to have the binary system, then you create a disk. So how much time does it pass before the creation of these, circumbinary disks? that you have in the simulation?
Well, so this whole simulation, it's very short, which is a disclaimer. It only runs for, under 7,000 years. So I forgot to put the time in here because I actually chopped this off from a different movie. But definitely by the end of a few thousand years, we seem to get this second binary disk. But it could also be dependent on the initial angular momentum of the cloud. So our cloud has pretty low angular momentum, and that's why the binary can kind of fall in quickly and do that. So if you have like a cloud with higher angular momentum, that interaction could take a bit longer.
Exactly, because in fact, my follow-up question would be a bit related also to your last slide, where you were saying the future work you would like to do. So, because putting these systems into a realistic, say, system where you have you have in principle also two body, system. So you have, encounters, cluster, you have a crowded field. So which is the impact in that case? It's complicated, I guess.
Yeah, definitely complicated. Yeah. So with this work that I was presenting, like the turbulence level that we have do agree with kind of observations of some cores, but we could have also made it much higher. But the problem that we were getting was we got too much fragmentation, and we wanted to specifically focus on binary stars just for this work. But definitely, I've already been running these zoom-in simulations, and we get much more complicated systems with many more stars interacting and tossing out things and disks being destroyed. So that's the next steps. And I guess the main thing that we want to do with these zoom-in simulations is you can only have so much resolution. So we're only really looking at the core fragmentation bit. We're just going to see, because stars can the core can fragment and the stars can fall into each other. So we're wondering how far down can core fragmentation explain this, and how much of it is attributed to disk fragmentation.
Yeah. Okay. Well, thank you.
Sorry, Giacomo.
No. I just wanted to thank and congratulations again. Yeah. Thank you.
So we have a question for Łukasz and then one from Dietrich.
Yes, then I'll just ask quickly, because for example, from other simulations from Michael Bate, for example, they show that multiples have considerably smaller disks, or at least less massive.
Yeah.
And I was wondering how does your models expand out? Because I'm thinking, in one hand, the episodic accretion should be a solution to our luminosity problem, right? And how massive are Getter disks? So basically, where in these models fall the formation of a disk, and how would it be influenced by those episodic accretion events?
Yes. Well, so after a certain period, we can't actually look at the circumstellar disks on our simulations, just because the sync particles are so close together and we only have so much resolution. But I do look at the size of the circumstellar disk environment that forms from these simulations in my 2019 paper. I don't really remember the specifics of that. But I'm sorry, could you repeat the question again? I don't know if I remember.
Yeah, so I was mostly wondering, if we get smaller disks from a binary system, doesn't it mean that most of the mass is being lost by those interactions, right?
It could be, yes. So I guess there is this dynamical radius. So from Lubo and Artemetz 1994, they kind of say that the circumstellar disks would be truncated at, the inner, so the circumstellar disk would be truncated at like, a third of the separation of the binary, depends on the eccentricity. So yeah, that would truncate the disk, but I guess where does that gas go to when it's being thrown out? Maybe it's being thrown out into a binary, second binary disk, or it's being accreted onto the stars. So that would be a good thing to follow.
Yes, thanks.
So now we have the last question. That's from Dietrich. You can unmute yourself and just do the question.
Yeah. I also enjoyed your talk. Really great work, very nicely presented. I'm wondering whether in these very young disks there could already be protoplanets, and whether orbital resonances between these protoplanets could also lead to instabilities of the gas disk. Has anyone studied that?
I don't know if they started at these very early stages. So these simulations are only run for a few thousand years, and I don't really know when planet formation begins. That would be a good point. But this is something that I am finding very interesting to figure out, because from observations, we are finding planets with multiple stars, and we know that stars, they can undergo these crazy interactions. So one thing I do want to kind of understand is under what conditions do disks in multiple star systems survive long enough so that we can make planets? So I've always kind of, at least because I'm simulating the very early stage of the star formation, I haven't actually thought about planets being in the disks, because I guess I don't think the planets would exist yet, but maybe they could, and that could be something to have a look at.
That's great. Thank you very much again, Rajika, for your presentation, and everyone for participating with your questions. I don't know, Giacomo, Łukasz, if you want to bring the session to an ending.
Yeah, just to thank again, thank you, Łukasz, thank you, Teresa, very much for chairing this session and for your patience, because of, as usual, sorry for the chat. I will learn why, and will not happen again, I promise. But also congratulations again to the speakers. Really, really great talks, and good luck now for this year, for your future. And I want to like to remind everyone that the videos will stay online, and that the CV and the details of our speaker, you can find also details to contact them on our program page. Again, www.eso.org/ESOHC. There you go, there you see the program. You can click on the title of the talk, and then you will be prompted with the CV and with details of the speaker, so you can contact them for questions. Again, thanks to everyone, and see you in a week.
Okay.
Bye bye. Thank you again. Bye bye.